Hello, today we're going to work on Chapter 8. If you can have your course back out and open, we're going to go ahead and get started. Chapter 8 is a little bit more about the big picture of taking and comparing samples to each other, so groups of samples to each other. And so here we are today. When we talk about comparing those groups of samples to each other, we're going to be introducing what we call the central limit theorem, and this is going to be the basis of what we do for the rest of the semester. So today we're going to introduce the central limit theorem for means. So this is quantitative data. So some important things for chapters 8 through 11, we're going to be inferring from a sample to a larger population, whereas what we did in the earlier chapters was more about descriptive statistics. So in other words, we are going to use statistics, namely the sample mean x bar or p hat, to make guesses and arguments about parameters, mainly mu, population mean, or the population proportion p. But to make that jump, we need to know a bit more about how samples and their accompanying statistics compare. This is called a sampling distribution. So how do samples compare to each other? So this is a simulation from a skewed population. So the population data is skewed right. And then you can see that we took some samples out of that skewed population. We took samples of size 2 and averaged them, samples of size 2 and averaged them. And this was their distribution, which was still a little skewed right. Then we took samples of size 10, and we found out that they were definitely much more similar to each other. And then we took samples of size 20, and look at how similar they are. So it says the moral of the story is, how does sampling means from a population affect shape, center, and spread? So the shape will be coming approximately normal. You can see that even if the population comes from a skewed distribution, our sampling distribution becomes normal. And our spread, first let's talk about our center. So our center will be, will stay the same for the most part, but our spread gets smaller. So you can see that it becomes normal, but it gets really small. Our spread becomes really small because they are not going to vary from each other much at all. Okay. So the next page says, let's take a simulation from a symmetric distribution. So we took samples of 2, 10, and 20 again, and our population shape started out symmetric here, with a mean of 16 and a standard deviation of 5. But you can see that our sample of size 2 is the one that's going to be coming, it's still symmetric, but it's still a little more spread out. But the bigger the sample size, so this is going to be a sample of 10, and then the one with the least amount of variation from each other is going to be the largest sample of 20. Okay. Okay. So it says the central limit theorem for means. Suppose there is a population of size n where mean, mu, and standard deviation sigma, a sample of size n is selected such that the following conditions are met. So the first condition is that we have to have a random sample. The second is that we have to have independence from the population. So sample observations are independent of the population. If the sample is collected without replacement, then the population must be at least 20 times larger than the sample size, shown here, where little n is your sample size and big N is your population size. Let's go down and discuss that a little bit. So faking independence. So this is without replacement. So if you were to go to the grocery store and you're going to grab a bag of grapes, and that bag of grapes is going to weigh some particular amount, but who goes to the store and doesn't try the grapes first, right? You just take one little grape and you're like, I'm just going to try it to see, make sure they're good and juicy or whatnot. And do you ever get up to the checkout and say, oh, by the way, when you go to measure that bag of grapes, I just want to make sure that you know that I ate one of the grapes, so it really actually weighs a little bit more than what it does now. They would probably think you're a little silly. And that's because if you take one grape out of that big bag of grapes, it's really not changing the average much, right? And that's what we're saying here is even though you might be taking a person out of the population, it's not changing the distribution much, but we have to show that here. So N is your sample size. Has to be less than 0.05 or 5% of the population size. But a lot of times we don't know the exact population size. And so if you divide both sides by 0.05, you'll find that 20 times little n less than big N is equivalent. Okay, so in that case, you can just say 20 times my sample size. Can I imagine that my population has to be bigger than this? And usually you can say yes. Okay. Another thing to note down here is that samples are always independent if we are sampling with replacement. So if you're replacing and you're sampling again, you're always good to go. Why is random so important? Because we're trying to avoid bias, right? So having a random sample is important. Bias. The third condition is the condition for normality, or what we call a normal curve or symmetric curve. So either the population distribution has to be normal, we'd have to tell you that, with no outliers, or the sample size is bigger than 30. So we'll either tell you it's normal, we'll give you a normal probability plot from 7.3, or if the sample size is bigger than 30, we don't have to worry. If these three conditions have been met, we can then describe our distribution of the sample means by the shape, center, and spread. And our shape should then be approximately normal. Our center should be the center of the population. So the center of all of these samples here, the mean of the sample means, should equal whatever you thought the population mean was. And then the spread, which is called the standard deviation of the sampling distribution of sample means, is called the standard error of the mean. So it's still a standard deviation, but it's got a new name called the standard error of the mean. And it is calculated by taking what you think is true about the population, that standard deviation, and dividing by the square root of n. It makes that standard error become smaller because you're dividing by a number. And as sample size goes up, you're dividing by a bigger number. And so that's why as your sample size gets bigger, your standard error keeps getting much and much smaller, because your samples, the bigger the sample size, the less likely your samples are going to be different from each other. Okay, so page 192. So we have this list of 50 colleges and universities in the US in 2020. And you can see here, we only have the top 4. The ... always tells us that there's more data we just can't see. They gave us information here in this little summary statistics. So it says the mean and variance for this data set is given in the StatCrunch output. Suppose you're going to take random samples of size 3 from this list. Assuming the requirements for the CLT are met, so we're assuming they're met, what would be the approximate standard error of the subsequent distribution? So the standard error is the SE of the X bar. It's the standard deviation of the X bar. So you're going to do this X bar lower is equal to the standard deviation of the square root of n. Okay. So it says, suppose you're going to take this, assuming they're met, find the standard error. So to do that, we have to have the sample standard, or we have to have the standard deviation, right? So that means we have to take the square root of this variance here, which is the square root of 1.1927244. That's e to the 8th, e8. So that's times 10 to the 8th. Okay. So we're taking the square root of this, which becomes 0.00019092. So this is 0.00019092 divided by the square root of 50, because there's 50 schools, and this comes out to be 0.000015. So you can see how small it's getting. So that's just one little calculation. We're going to look at some bigger problems here. Okay, so it says a graph of sampling distribution is shown. Here we go. A graph of a sampling distribution is shown here. Answer the following. What is the value of the mean of the x bars, and what is the value of the standard error or the sigma of the x bars? If the sample size is n equals 15, explain what is likely true about the shape of the population. Okay. So we're going to look at the center here. So it looks like the center is about at 123. And then it looks like these are going to be our markings here. So it looks like the standard error is from 117.6 to 123. And so the difference here would be one of the standard errors. So that would be 5.4, because this is the sampling distribution. So it says if the sample size is 15, explain what is likely true about the shape of the population. So sample size is 15, which isn't real big, and the sampling distribution looks normal, so the population is probably normal. Otherwise, it would still look a little skewed. If the sample size is n equals 15, find the approximate standard deviation of the population from which the sample is drawn. So we know from the formula given that the standard error is equal to the standard deviation divided by the square root of n. And from this problem, we already know the standard error is 5.4. We want to know the population standard deviation, and our sample size is 15. So if we multiply both sides by the square root of n, we can see that the standard deviation of the population is about 20.9. So for future reference for yourself, if you don't know the standard deviation and you only know the standard error, you can just take the square root of n times the standard error, and that will give you the standard deviation of the population. So in our course pack, there is this decision matrix on what we know and what we want to find. But using StatCrunch, we found in Chapter 7 is much easier, and we don't really need the matrix as much here. But remember that if we want to find a percentile or an X bar, then we are going to go backwards. So if we want to find area or percent or probability or percentile rank, then we're going to use our X bar and our quartile to find that. Otherwise, we're going to put in our percentile or our X bar, and we're going to use inverse norm. Okay, but I'm going to show you in StatCrunch. So it says, suppose the sample of size n equals 38 is taken from a population that has mean 250 and standard deviation of 50. Find the following. Don't worry about the calculator entry so much. We're going to do this all in StatCrunch together. But I do want to see a shaded graph. So it says, describe the sampling distribution. So we're going to assume the CLT have been met. So assume CLT, okay? So our shape is going to be approximately normal. Once we've met the CLT, we can always say our shape is approximately normal. And then our center is going to be the mean of the X bars, which is going to be the mean of the population, which we said was 250. And then the spread is going to be the sigma of the X bars, which is going to be sigma divided by the square root of n, which is 50 divided by the square root of 38. And if you put that into your calculator, that comes out to be 8.11. So now when we go into StatCrunch, just like we did in Chapter 7, we're going to use 250 as our center, our mean, and our standard deviation is going to be 8.11. Okay, so this is what we're going to put in. And now we're going to find, we want to find these probabilities. So for the first one, it says, find the probability that X bar is less than or equal to 240. Well, we know our center should be at 250. And we want to know that something is less than 240. So we're going to mark 240. And we're going to shade to the left. Okay. So when we go into StatCrunch, we're just like we did in Chapter 7, we're going to say the probability that X bar is something, right? Some kind of inequality compared to whatever that is. And this is going to equal the probability. We also call that area, right? And then our options for this right here are going to be less than or equal to or greater than or equal to. Remember when we talk about continuous data, you can't have just an equal to. So we're looking for this area right here. So let's go ahead and check out StatCrunch. So in StatCrunch, we are going to stat in calculators. So stat in calculators, and then we're going to the normal curve, just like we did in Chapter 7. And so our normal curve, we have to tell it what our parameters are. So our mean is 250 for this situation. The standard deviation is what we call now our standard error, 8.11. And then our situation is a less than or equal to, but we want to find what is the probability it's less than or equal to 240 and hit compute. And it comes out to be 0.1088, which is 10.88%. So let's try to do the next one without seeing the picture. So it says, find the 95th percentile of the sample means. Okay, so this one is the same mean and standard deviation, but this time we know the percentile is 0.95 right here. And percentile is always from the left to the right. So when we hit compute, that's shading at 95% of the data is below this value. And that value comes out to be 263.34. So that X bar, the mean would be 263.34. And I'm going to shade my graph. And I'm going to take you there so you can see what it will look like. So you can see here that we didn't know what this was. We just knew that this area or percent was 95% probability. Okay, so when we typed this one in, let's just write, we said the X bar is less than, and we didn't know what, but we knew it was equal to 0.95 because that's our 95th percentile. So the next example is one of my favorite examples. We're talking about some old pennies. So it says, in the US, the year each coin was minted is printed on the coin. To find the age of a coin, simply subtract the current year from the year printed on the coin. The ages of circulating pennies are right skewed. Assume the ages of circulating pennies have a mean of 12.2 years and a standard deviation of 9.9. So when we say right skewed, it's because there's very few pennies out there that are old. Most of our pennies are younger because they stopped making them out of the pure copper. Okay, so it says, what is the population? And that's all pennies in circulation. What is the sample? And that would be pennies in sample. What is the sample size? So we said we took a sample of n equals to 40. Right there it is. Is the variable age of penny qualitative or quantitative? It's quantitative and it's measured. So it's actually continuous. Which type of observational study is conducted here? So we're not comparing anything in a case control, and we're not following over time. So this would be cross-sectional. Okay. Verify that the conditions of the central limit theorem are met. So the first one is, do we have a random sample? And they did tell us that they took a random independent sample. Now, independent means that pennies are independent of each other, but our independent requirement here in the CLT is independent of the population. And so we are without replacement because we can't pull a penny and then pull it again, right? So it's without replacement. So we have to prove, so I'm going to say 20 times, and I have to prove that it's less than my population size. So 20 times 40 is 800. And I'm going to put a question mark there, and I'm asking myself, do I think that my population size of pennies in the whole US is at least 800? Yes, I think we can safely give that a check mark. And then our third question is for normality. They didn't tell us it was normal, but n is equal to 40, which is bigger than or equal to 30, so we're good. So then it says, describe the sampling distribution of the sample mean, giving the shape, center, and spread using symbols. I'm going to have to. Okay. our shape here, we can then say is approximately normal. Our center is going to be the mean of the x bars is going to be the mean of the population, which we said was about 12.2 years. And the spread is the sigma of the x bars, which we said is the sigma divided by the square root of n. So we said that would be 9.9 divided by the square root of 40. And to make sure everybody knows how to put this in our calculator, we are going to take 9.9 and divide by the square root of 40, and that comes out to be 1.565. Okay, so let's answer some questions about our pennies. So the first question says, using now in, we're going to use this in StatCrunch. 12.2 is our years. And then for our standard deviation of the means, our standard error, right? We're going to put in 1.565 to answer these questions. So let's draw the picture in the first one. It says, find the probability that the sample mean is between 10 and 14 years. Okay, so if the mean is 12.2, that means 10 and 14 are going to be somewhere in between here. So we're going to use a between in StatCrunch, right? Just like this. And we're going to find out what that is. Let's draw the other pictures while we're at it before we go to StatCrunch. So this one says there is a 20% chance that the mean age of 40 random pennies will be at or below what? So 20% chance means that we know probability. Okay, and it says at or below. So that means the sample mean is going to be at or below something, right? And that's equal to 0.2. So we need to know what that is. So that means 20% of the pennies are at or below some average age of those 40 pennies. Question mark. Okay. You have 40 pennies in your car. Would it be unusual if they have a mean age greater than 16 years? Okay, so we're talking about greater than this time. So the probability that the average of those 40 pennies is greater than 16 is what? So we're going to find out this. So there's our 12.2, and we want to find out what is the probability that they are older than 16. We're looking for this. So let's go to StatCrunch and find the answers to these three questions that we just came up with. Okay, these are our three questions, and we're going to put this information into StatCrunch, 12.2 and 1.565. Okay, so we have to change our scenario here to 12.2 and 1.565. And our first one is a between. So we have to go up here and click on between. And we're going between 10 and 14. And there it is. It says 0.7950, 0.7951. So about 79.51% of the pennies are between 10 and 14 years old. We would expect that. The next one is a less than or equal to, and we don't know what this is, right? We said, but we do know that 20 is 20% of the pennies. And we want to find out what value. So this does match our picture. And that value would be an average age of those pennies we would expect to be about 10.88 years. Make sure you put units on there. And then our last picture was a greater than, so we have to change that. And we said, what is the probability that they're greater than 16 years? And that comes up to be 0.0076, which is about 0.76%. So it says, would it be unusual? Yes, because I'm going to show you on my paper here, it would be unusual because 0.0076 is less than 0.05, which is less than 5%. So yes, it would be unusual. It says, suppose the pennies in your card does have a mean age greater than 16 years. List 3 conclusions you might draw with explanations. Okay, so I guess it could be, maybe we, sorry about that. Maybe we didn't actually have a random sample. So not a random sample, some kind of a bias sample. It could just be a fluke, right? So could be a fluke, that's a possibility. Or it could be maybe the population parameters are not correct. Not correct. As in maybe the mean is really not 12.2 years for pennies. Maybe it's really actually older. Okay, so that's our introduction to chapter 8 and comparing samples to each other. And the big takeaways from chapter 8 are passing our central limit theorem, random sample, independent of the population, and a normal distribution. If you've met those 3 criteria, you can then state your shape, center, and spread. Remember, the big thing that's changing is our standard deviation of the means, which is called the standard error, is actually going to be this adjusted. It is going to be smaller than our standard deviation. And we're going to use that along with the mean in StatCrunch to find our probabilities. So catch you back for 8.2.